Okay, so this is a supplementary video. You don't have to watch it, but you're here, I suppose, if you're hearing these words. The purpose of it, though, I think will allow you to develop a little bit of an intuition about what's going on in an induction motor. Remember, the induction motor is a motor that is by far the most common type of AC motor out there and is in everything, if it's almost everything, if you're thinking about something that contains an AC motor. And there's a lot of AC motors out there because our whole power grid, well, with some exceptions, runs on AC. So if there's a motor in your household, for instance, that's probably an AC motor. And if you're talking about a motor on the ship, that's probably an AC motor because the power grid on the ship is AC. And if you're talking about a factory, probably all the motors in there, with perhaps a few exceptions, are induction motors as well. And I wanted to show you the sort of torque. So torque is here, right? So that tau is torque, okay? And rotor speed on the x-axis, all right? And we can get a little bit more of an idea of how torque is related to rotor speed and how it's related to slip and things like that. And the two curves that you're seeing on this set of axes are just two curves for two different induction motors. They're both induction motors, two different designs meant for different things. This one here, so we'll call it curve number 1. There we go. That one is one that operates typically with a higher slip and is better for things with variable mechanical load, stuff like that. And then this curve, the one that sort of goes up and then drops off, we'll call design number 2. That one's also very common. And there's a few other classes of induction motor as well that, if you're so inclined, you can look up, okay? But let's concentrate first on curve number 2. Well, either of them, really. And this, okay, for both motors, all induction motors, if you have the motor speed actually at the synchronous speed, and I got that slightly offline, but right there where it intersects the axis. So you've got torque. This is the 0 of speed and the 0 of torque over here. So this right here, okay, what speed would that be where the torque is 0 and yet the speed is quite high? Okay, you might be able to hear my upset child in the background, but hopefully that didn't disturb your thoughts about that. Okay, you should have come up with high speed, 0 torque. Well, that has to be the synchronous speed of the motor, right? The speed of rotation of the magnetic field around the stator, okay? Because if the rotor speed is exactly equal to that, there can't be any torque because you can't induce any voltage on the squirrel cage, and thus you can't produce any current. And if you don't have any current, you're not going to have any torque, okay? So that's the synchronous speed. And you'll note that no matter what the design of the motor is, whether you have a torque versus speed curve that looks like this one, or whether you have a torque versus speed curve that looks like this one, they both go to 0 at the synchronous speed. Okay, so that basic fact is always true for an induction motor. So a couple of other things. This curve number 2, right about there would be the peak torque. Okay. And that kind of motor is generally designed to operate to the right of the peak torque, usually a significant amount to the right of the peak torque. Because when you're developing peak torque, you're generally also developing pretty close to the peak amount of current in the windings, well, not the windings, but in the squirrel cage, in the bars of the squirrel cage. Okay? if you were to plot, say, current on here, so let me write it in red, okay? Then the current curve for both of these would kind of look like max, 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 really big, really big, really big, and then would drop off precipitously and go to 0 right at the synchronous speed. Okay. Okay. So, and as for why these motors, particularly design number 2, would be designed to operate to the right of the peak torque, whether you're talking about peak torque over here for design number 1 or whether you're talking about peak torque over here for design number 2, is because, well, if you were to put a mechanical load on the motor, say for instance, we are operating right here. So at that speed, say this is our operating speed, sort of what it's designed to do. It's steady state speed, what it's going to be doing for whatever standard mechanical load it's designed to drive, a fan or a set of gears that then connect to like machinery that's going to smash something, who knows what, okay, a crane. So whatever the case may be, operating speed right there, let's say it's designed to do that. And so it intersects this curve right about there, okay, and this curve right about there. But in any case, whatever that operating speed is, not really that important, okay? But what you want in a motor is when you get more resisting torque. In other words, remember, this is the torque that's being produced by the motor. And if you're operating at a steady speed, that means that the net torque on the motor must be 0, right? The resisting torque must balance exactly with the torque developed by the motor, and then you're not changing your rotational speed, right? You'll just stay at this operating speed here, okay? So, where was I? Oh, right. So if you have a situation, though, where something goes wrong, okay? So I don't know what you want to think about that as, but say something goes wrong and you get some, sand in the bearings or something like that, and suddenly you have quite a bit more resisting torque than you did before, okay? Or maybe if you're driving a propeller, it gets fouled with seaweed, and suddenly there's a lot more resisting torque than there used to be. So what you'd like from your motor is for it, when you drive this, its operating speed this way, okay, well then you'd like the torque developed by the motor to increase. So if we were to say drop the speed of the rotor down to, I don't know, like here, okay, if it drops down to that speed, okay, well you can see for both designs, okay, both for design number 1 and design number 2, when you drop the speed, the amount of torque that you're developing is much larger, okay? And so it's trying to drive, it's trying to balance out that resisting torque. If it's something temporary, maybe it overcomes it and it goes back to the usual resisting torque, in which case the motor will speed up again and come back down over here and back to its operating speed. If it stays on there, right, you can't get rid of the seaweed, or something is breaking and so it's not likely to go away, it's only going to get worse or something like that, well then at least the torque developed on the motor will balance that extra resisting torque and give you a chance to sort of figure something out to do about this situation before you, in this case, go down. If you go farther down in speed, well then now the torque developed by design number 2 actually goes down. Still a lot of torque compared to sort of typical operating torques, or at least comparable to it, the way I've drawn it. But if you get back up over this peak, well then now the torque developed by the motor is actually less, and then the acceleration, the braking on the motor will accelerate, because as long as the resisting torque is still greater than the torque developed by the motor, then it's just going to slow down. The speed keeps going down, so the torque keeps going down for design number 2. Design number 1, the way that it's constructed, well, you just keep increasing the motor torque as you decrease speed, right? You keep going up this curve. because the design number 1 develops its maximum torque when it's at 0 RPM. Right? That's actually a nice thing, right? You're really going to give you a lot of torque when you're getting started. That's what you need. Usually design number 1, though, lacks a little bit in efficiency compared to design number 2, which is why there's 2 designs. You don't just design everything to be design number 1. It comes from the fact that if you want design number 2, you have, I believe, low resistance in the rotor, and design number 1, you need higher resistance in the rotor, but that means that you are you're frittering away more energy in the terms of heat, and that energy is coming from somewhere and has to come from the electrical energy that you're putting into the motor. All right. So this is the basic idea. So you have these peak torques wherever they happen to be. The motor operates to the right, so at higher speed than the peak torque it occurs at, and this difference right here between, say, the operating speed, the typical operating speed, and the synchronous speed, that, at least in RPM, would be representative of your slip. Okay? So that's that difference between the operating speed, so the actual rotor speed, and the synchronous speed, the speed of rotation of the magnetic field around the stator. And you can see as slip increases, so as you go down to, say, this point, so that lower rotor speed after we've done something or something has happened to the motor, well, then slip is bigger, right? The gap between the synchronous speed and where it's operating is much larger in that situation. And in both designs, you will develop even more torque. Now, in design number 2, well, if you were to actually drop the speed any lower, any really big resisting torque that overcomes this maximum torque that it can develop, well, then now you're in trouble, okay? Because if that resisting torque doesn't go away, then the rotor will continue to decelerate. The torque it develops will actually go down somewhat, and yet you'll still have this maximum current going through the squirrel cage, and that can cause damage if that current continues to flow in the squirrel cage bars that way. All those squirrel cages are designed to allow this amount of current to flow through those bars for a short period of time, right? You have to get from 0 RPM to the operating speed somehow when you are starting up an induction motor, right? And that necessarily means that there's going to be large amounts of current for a little while. But if you just sit there at that maximum current, and the rotor has become locked, or the rotor is moving really slowly compared to its operating speed, normal operating speed, then you might start melting things, and that's never good for an electrical appliance. Okay, so this hopefully helps clear up a few things, extend your knowledge a little bit about how torque and rotor speed and current and all that kind of stuff is related in an induction motor. And this will be the last bit of AC motor stuff that you'll see from me. And the next thing on the docket is a little bit of electromagnetic waves and AC circuits as they relate to a basic radio receiver. So look forward to that, probably starting sometime tomorrow afternoon. All right, see you then.